Hello everyone, let me present to you our work, Targo and TargoNet, benchmarking target-driven grasping under occlusions. This work has been recently accepted at IJCV 2026. In the real world, a target object is often occluded in clutter scenes. This visual occlusion creates a fundamental challenge for target-driven grasping. Current methods realize the occlusion challenge, but often avoid it by either moving the camera to the next best view, or removing the occluders before reaching for the target. In this work, we confront the occlusion challenge. Given a single RGBD view, our target-driven grasping method, TargoNet, directly grasps the target even under heavy visual occlusion. To understand how direct target grasping is done, first we introduce two concepts, single scene and visual occlusion level. The clutter scene includes both the target, here the cleanser bottle, and occluders, whereas a single scene contains only the target object captured from the same camera pose. To quantify how much target is occluded, we calculate the ratio of occluded pixels in clutter scene divided by the total pixels in the single scene. With occlusion level and single scene, we build Targo synthetic training dataset using VGN objects. With random placement strategy, we generate scenes mostly with low occlusion levels. Note that we sample grasps from not only clutter scenes, but also single scenes. The reason is explained in the next slide. In the Venn diagram, we show three sets of successful grasps. C is a set of successful grasps in clutter scene. S is a set in the single scene. Then, S minus C denotes the set of grasps that succeed in the single scene, but fails in the corresponding cluttered one. By including these occlusion-induced failed grasps in training, the model explicitly learns how occluders affect feasible grasps. The single scene grasp augmentation alone yields at least 5% boost for baseline methods and 10% increase for our TargoNet. We also build a balanced test set because standard random placement creates mostly scenes with low occlusion levels. Evaluating on such easy scenes would overestimate model performance. Instead, our benchmark provides 1,000 scenes for every occlusion level from 0 to 0.9. Evaluating existing sorted models on our occlusion-aware balance set, such as VGN, Giga, EdgeGraspNet, and ICGNet, we found a clear trend. Grasp success rate drops by up to 20% as visual occlusion increases. This confirms that visual occlusion is a major failure mode for target-driven grasping. But how do we stay robust under high occlusion? Our solution is TargoNet. Given RGBD input, we first segment the visible target, then complete the missing geometry, and reason about the full target within the context of the full scene. First, both the scene and completed target are encoded into point features with a 1D CNN. Then, our key module, Target Scene Transformer, or TST, fuses the information of scene and target features with cross-attention, so that scene features identify feasible target regions, and target features understand how occluders block the target and constrain feasible grasps. After feature fusion, the 3D feature grids are projected into 2D feature planes to reduce memory and computation, and refined by a 2D UNet to integrate local details and global context. Then, an implicit affordance decoder predicts for each grasp center, grasp quality, grasp orientation, and gripper width. Finally, a collision-free grasp is selected with the highest predicted grasp quality. By jointly reasoning about target geometry and scene context, TargoNet achieves robust performance even under high visual occlusion. In Targo synthetic test set, TargoNet is remarkably stable, dropping by only 7% even at extreme occlusion levels, while other sorted methods drop by 20% or more. In real-world panda-arm experiments, the gap is even clearer. While baselines like Giga decrease by 40% in performance from easy to hard scenes, TargoNet remains robust with only a 13% drop. These videos demonstrate TargoNet's robustness in action. For more details and to access our paper, code, and dataset, please visit our website. Thank you.